Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mayo, and I'll be helping moderate today's webinar, Parallelizing Data Science with Julia. In this webinar, we will learn about the multi-threading capabilities of Julia, how parallel computation can speed up common data science workflows, and using the power of JuliaHub as a convenient computing platform. We'd like to have some interactive session today, so please write your questions in the chat. We'll either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce today's presenter, Dr. Elliot Saba. Elliot is a senior research engineer at Julia Computing, where he designs next-generation tools for the Julia programming language. Dr. Saba received his Ph.D. from the University of Washington in electrical engineering in 2018, specializing in digital signal processing and machine learning. Please welcome Dr. Elliot Saba.
Hello, everybody. Good morning or good evening, depending on where you are. As Eric introduced, thank you for that introduction, Eric. We're going to be talking about parallelizing data science with Julia. We're going to be focusing more on the parallelizing part than the data science part, assuming that you all already have interesting things that you want to do with your data. But we will be going over a few of the more basic syntaxes and having a toy problem that we can play with, just so that we can all see what it looks like, what it feels like, and most importantly, how to answer the question, how do I speed up my code using the parallel capabilities in Julia? Now, the basic workflow for all data science workflows is basically going to be you have your data, you do some processing on it, and you get some results. And there are different areas in which you can parallelize or speed up the different building blocks in these workflows. But we're going to be looking mostly at the data and processing portions. And between those two, by far, we're going to be looking at the processing and seeing how can we make use of the abundance of compute hardware that computers can offer us these days. Now, whenever you're parallelizing some piece of code, there are some questions that you have to ask. And really, the takeaway from this webinar is going to be giving you guys the tools and the proper mindset to be able to answer these questions. Things like, well, first off, you want to make sure that your program is working correctly. But the next question that you want to ask is going to be, what resources is it currently bound by? There are many different bottlenecks that you can have in a computation. Is it that your data set takes a long time to read in from disk, and that's actually the thing that's bottlenecking the computation? Is it that you have some very serial operation that you are performing on your data that takes a long time? Is it actually the writing out of the results at the end that is the thing that takes the most time, etc.? And so figuring out what resources your application or your data processing pipeline is bottlenecked by is going to be a critical first step in figuring out how we can parallelize and speed up a certain data science workflow. Again, whether the operations are inherently serial or are, as we like to say in the business, embarrassingly parallel, that's the best case. We like that a lot. And then once we know that there's something that can be parallelized, what parallelization approach should we use? There are a couple different ones available to us in Julia. We're going to be focusing on threaded parallelization in this webinar. Previous webinars have looked at the GPU capabilities, which also are a good way to speed up your parallelizable sections of your code. And then finally, how can we measure how successful we are in our parallelization? If we expend a lot of effort to try and transform our program into something that uses a lot of parallel hardware, can we actually measure how much end-to-end speed up there is? You know, what's kind of the business impact of our effort? As I said, we're going to be focusing on thread-based parallelization tools in Julia, and really we're going to be looking at these two. There's this thing called threads.athreads, which works with for loops, and it's extremely simple to use. But for more flexible workflows, for more complex things, we're going to be using this thing called threads.spawn. As you can see, we're going to be getting into code very quickly here. In order to make this as easy as possible for others to reproduce and replicate, we're going to be doing it all on JuliaHub, which is our convenient platform for compute using Julia. It's got a pre-installed system and everything. There is code at this Git repository that I will paste into the chat right now. So if anyone wants to try and replicate this after the fact, you can. And what we're going to do is we're just going to go onto JuliaHub, and we're going to start looking at some code, and we're going to walk through a simple data science application, and then we're going to see what Julia offers us, what JuliaHub offers us, and then we're going to start parallelizing things and see if we can speed up our toy problem a little bit. So I'm going to move this window off and enter the JuliaHub interface. Now, if you yourself were to go to juliahub.com, you would see a Run tab here on the left. All I have done is gone here into Run Code. Let me log in real quick. Sorry, into Applications, and there is a Julia IDE, the full power of VS Code in the cloud section. I have launched an instance, and after you've launched it and configured it with a particular hardware setup, it looks like this. You can choose how many CPUs you want, how much memory per CPU. You can limit the amount of time that it's allowed to run in the event of a runaway job. You don't want to overcharge yourself, etc. And once you start it, you'll be able to click this connect button, and it will take you to an interface that looks like this, where you can add source files over here. You can edit them, you can run them, etc., etc., etc. So what I've done here is I've set up that code in that repository that I pasted into the chat. And the first thing we're going to look at is just this simple data science file. Now, data science is often exploratory, often analytical. We're going to be doing a little bit of both here. We've got a, sorry, did someone ask something?
Can I ask you just to possibly increase the font a little bit?
Oh yeah, absolutely.
Thank you so much.
Is this good?
Much better.
Great. And actually, let me see if I can full screen this to get the maximum viewing portion. Great. So for those of you who haven't used VS Code before, I've got kind of the organizer over here. I've got a tabbed window here with different source code files. I've got a plots pane where plots will show up, and I have a REPL and terminal down here. So I can switch between, for instance, a bash terminal that is showing, allowing me to do commands on the command line, and also an interactive REPL where when I run things here, say if I run this block, it will run it, and whatever value gets returned from this block, in this case, it's just the implicit return of the last line here, which is pi/3, it prints it out. So what we're going to do is we're going to do some, arbitrary data science stuff. We'll create some data that's just a bunch of random noise, and it's shaped in a certain way so that it creates kind of a nice blob, and we'll plot it. Here I am using the plots library to create a scatter plot of the first 2 dimensions of my data. And I'm just saying, okay, I have some arbitrary feature 1, some arbitrary feature 2, and I have constructed it such that it gives me this nice blob here with a title and labels and all that good stuff. A common, for instance, data science thing to do would be to calculate PCA on this. Which we can do with the multivariate stats. The multivariate stats package, it gives us a fit with PCA function here. So we'll run that. When we run it, you can see down here the REPL prints out the thing that is returned from whatever code block I just ran. So in this case, it's that M object. I could also down here just type M and get the same thing. I can interactively explore things down here. We can look at, say, the mean value that it calculates for this particular data set, which should be close to 0. In fact, it is, because the mean of my value is here. And then we can do things like take this and use it in further code blocks. So here I can plot the data with the PCA vectors overlaid, those directions of maximal variance that PCA finds. So it says, all right, your principal variance component is in this direction, and the next largest one is in this direction, etc. So this is the kind of interactive workflow that I like to use when I'm doing this kind of data science, this kind of analysis, especially in VS Code, which I find is a pretty convenient tool to use for this kind of stuff. Let's take a step forward. I don't really want to dig into the specifics of this, and in fact, I don't want to dig into the specifics of much of this because most of the specifics are going to be specific to whatever problem you are trying to solve in your application domain. But let's create ourselves a toy problem, something that takes some time to calculate, it reads in some data, et cetera, and actually gives us something to work with, something that we can do, that we can use multi-threading to speed up. So instead of creating this data and plotting it, what we're going to do is we're going to create some data that is slightly more interesting and that we can process. So we're going to create some data that is just a bunch of random sinusoids that are wiggling about and that we can write out to large CSV files. I have this file here, CSVgen, which is going to use packages such as CSV and data frames and DSP and such in order to build this data for us. So we're going to generate 30 files. Each file is going to have 200 sinusoids. I'm splitting it into kind of a small and a large toy data set. The reason being, when we eventually want to run this, we'll want to run on the small data set first, just to make sure that our code actually works, to get a good idea for it. And then we'll run it on the large data set in order to get more accurate timings, because our workloads will be more representatively large in general when we're doing stuff in Julia. At least we hope so. Got some other parameters here to set characteristics of the data that we're creating. So I'm just going to get rid of these plots and run some of these. So I have some helper functions here that generate these sinusoids that walk around. This isn't terribly important. The most important thing is that we're going to take a look at what these things that I'm generating look like. So each of these files is going to have a number of sinusoids that are slightly randomized in frequency and amplitude. They will be shaped by an overall modulation curve that basically just makes them look interesting. So it's not just random noise. So this is an example of 3 of the sinusoids plotted together. You can see they're oscillating up and down very quickly, and they're also kind of all shaped by this overall modulation curve. They're also not centered at 0. They're shifted around a little bit. And so they just make something that's kind of interesting. If I generate more and more of these, we can see this is kind of the representative data that we're creating. And when I run this file here, this chunk here, to write them all out to disk, what's going to happen is it's going to generate files and write them out to a place predetermined on the disk. In this case, I'm using a package called Scratch, which is the thing right up here. Scratch provides what are called Scratch spaces. They are stored within your .julia directory, and they're made for things that are kind of temporary. Things where if it were all to get erased, that's OK. You can regenerate them. So you can see here the output directory is being set to this get scratch call with generated CSV small. And right up here, I have the Scratch directory opened, and we can see all the CSVs that it's creating. We can actually open up one of those just to see kind of what it looks like in VS Code. And you can see it's got these things called trace1, trace2, trace3, et cetera, all the way up to the maximum, which is 200. And then we've also got the modulator, which is that overall curve that we're saving as well, just as a kind of data set. And we've created 30 of these. So if we were to take a look, how much data is this? This is each of these CSVs is about 40 megabytes large. So 30 of those, it's a couple hundred megabytes. Not too big. Something that is large enough that we can actually play with. And so now that we have some kind of toy data set, now that we've written it out to disk, it's in a format that we can deal with, let's actually look at something that we can do with it. So I have 3 pre-made analysis pipelines here that are all doing the same thing, but they're going to do them in different ways. One is going to run it serially, and this is very simple. We say the CSVs are coming from here. We want plots to go out to here. We want to have a for loop over the CSV files, and we're just going to load the CSV, We're going to process the data using a kind of arbitrary definition of what processing is. And then we're going to plot the data, and we're going to save it out to a file that is going to go into that plot directories. And we're just going to see kind of how long that takes. Now let's dig in real quick to see what we are actually processing, what we're actually doing. And then we can see how long it takes, how much time we're spending in different areas, and what the best approach would be to speeding up this data science workflow, which is a very common one where we're just reading in CSVs, we're processing them, and we're generating reports out so that the human or some further algorithm can take a look at what's interesting, what's going on inside of our data. So inside common, this is where all of these functions are going to be defined. You can see that I'm including that code right up here. We have a couple helper functions. So load CSV is very simple. It just uses the csv.read function. In this case, I am actually disabling threading inside of it because Julia, being a language that has nice composability, even with threading, different pieces of the runtime, different packages can have multi-threading enabled within themselves. We're going to actually purposely disable that for now, just so that we can see what it looks like, and also so that when we want to load multiple CSV files in parallel, we can control how much threading is happening there. In my experiments, loading these 40 megabyte files, CSV is only going to use 2 threads anyway, whereas I have a total of 8 cores in this machine. So the difference here is fairly small in any case. But if you were to load a much larger CSV file, having threaded equal to true here would actually be, which is the default, it would actually be pretty beneficial when loading an extremely large CSV file. We have our process data function, and what this is basically going to do, we should uncomment that. What this is going to do is it's going to call PCA to fit some traces. And then it's also going to do some purposely serial code to just calculate which of these sinusoids correlates best with one of its neighbors. The reason we're doing this is because, one, it's a potentially useful data science workload. It's the kind of thing that you might be doing in your own code. But 2, this code right here is not written to be parallel at all. It's got these 2 for loops. It's doing these correlations. It could be parallel if we were to parallelize it, but we're purposely not going to. We're going to keep it serial. And the reason is because we're going to explore how these different workloads, this PCA versus these for loops doing correlations. This correlation, by the way, is just a sample correlation measure. You can look it up on Wikipedia. And we're just trying to find kind of the, we're doing different kinds of work on these CSV files. And then in the end, we just return things like M, that trace, that modulator trace, that overall shape, the envelope that we found, and then also M hat, which should be something similar to M, but it'll be an estimate and it'll be kind of corrupted. And then we have the best pair that we find here, the 2 sinusoids that look the most alike to each other. And then finally, we have our plot data function, which is going to take in basically all of the information that we've had so far, the file name, the overall data frame, the CSV file in a table format, M and M hat and best pair, which are the things that we found in process data. And then this is just going to plot it out. It creates a nice little plot and saves it out. So let's run it manually just in our REPL first and see if we understand what's going on. So in here, we are going to include all that common code. Let's switch down here back to the REPL. We will get these values. So you can see it's saying things like, oh, the CSV directory is this directory, and the plot directory is this directory, etc. We've got all our CSV files. And then this for loop here for F in CSV files, we'll just say F is the first value in CSV files. And now we can do things like we can run df equals load CSV F. So this is using the CSV and data frames packages. So what I'll get back here is an actual data frame. Those of you who are used to data science, and especially things like pandas, will be very familiar with how you perform operations with data frames. So we've got a nice little tabular output preview here. You can do things like, say, df.trace1, for instance, in order to get that first column. You can also do things like give me the first 100 values of trace1, and it will slice it accordingly, etc. It's a nice tabular data format with named columns and all that stuff. Next, we're going to process the data. So when I run this, it's going to run that function that we saw, which calculates PCA and does this kind of column-wise matching and such. And because it's returning multiple values, when I run it in the REPL, it kind of bundles them together into this tuple, which is a little difficult to read. You can see it's got this open parentheses here and this closed parentheses here, and it kind of gives you a string representation of the first array, which is that M, and the second array, M hat, and then best pair itself is also a tuple. Not particularly easy to read. However, if I were to look at M or M hat directly, it's much easier to see. Finally, if I were to take this and pass it off to plot data, it will write it out to disk, but because I'm running it directly, it will also plot it here. And so what we see here is we see essentially we've got M, which is this blue line. We've got M hat, which is supposed to be something similar to it, and it kind of follows the same direction, the same overall shape of it. So I'm satisfied with that. It's not this is not a rigorously defined problem in any case. I'm just throwing a bunch of data at things and choosing things that look more or less like a real data science workload. And then down here, we've got, it found two sinusoids that correlated very well together. And we can see, yes, in fact, they do correlate quite well together. They have basically the same frequency, basically the same phase. And of course, all the sinusoids have the same modulation envelope. So we expect them to increase and decrease like that. So yeah, that looks really good. And it says this pair is trace number 17 and trace 41. Great. So this is the kind of analysis that we're doing. Now, if we were to run this whole thing, so I'm going to switch to a terminal. And I'm going to run Julia using the current project to run serial. So when I run this, it's going to run the entire script. And I have some timing code here, such as this t processing equals at elapsed. And then it contains this entire code chunk here. And then at the end, it will print out, oh, I finished processing this many files in this many seconds. Now, while this is running, I'm going to open up a second terminal. I'm going to start top, which is basically a activity monitor for the Linux command line. And what we can see is that Julia is busy here, and it is nailing a single core. So we can see that it's using about, give or take 1 core's worth consistently. Now, right now, all it's doing is it's loading the packages, things like the plots package, the data frames package, the DSP package, etc. And then it starts getting on to the work of actually processing the CSV files. But even while it's processing, it's still only using about 1 core. Now, what we'll see is every now and then, it should spike up. So you can see, I don't know how easy it is to see on Zoom, but every now and then it's spiking up to maybe 500% or 400%. Oh, there it got up to 700%, etc. So what this means is that the majority of our work is single-threaded. However, every now and then, there's something that we're doing that is more than just single-threaded. It's using multiple threads. If we were to investigate, we would be able to eventually find what the pieces are that are serial and are parallel, but I'll just skip to the end so that we don't have to do things like comment out code, run it again, or dig through the source code to see what is spawning extra threads. The answer is that the great majority of BLAS operations, matrix operations in Julia, are going to be using a BLAS library backend, like OpenBLAS or MKL. And these libraries are already quite highly tuned to use multiple threads, because it's so important to be using multiple threads for these kinds of dense linear algebra workflows. And so this PCA right here, this is actually using BLOS operations internally. PCA involves many matrix operations, and so each of those matrix operations individually will be parallelized across that single matrix. If I am to comment this out and simply add kind of a placeholder value for m hat, and I were to run this again, what we will see is the CPU usage will not spike above 100%, or at least not appreciably. This is a classic example of a workflow that is some part serial. So this stuff down here is all serial. It's all going to be running on a single thread, and some part parallel. So this PCA stuff is kind of inherently parallel because it has a library itself that is using multiple threads. Why do we care about this? We care about this because if my workload was primarily things like this PCA, then adding extra parallelization on top won't help that much. It will help some, because nothing is perfectly parallel, and if you can have multiple pieces of work running at a time, then they can be scheduled overlapping a little bit, et cetera, et cetera. It's good to kind of fill your CPU pipelines with instructions so that they always have something to work on and you're never sitting around waiting for stuff to happen. But you won't get like an 8 times speed up by running on 8 cores, by running 8 things at a time, if each of your individual chunks of work is already using 6.5 of your cores. So we can see here where we're processing the CSVs and we're never spiking above 100. Fantastic. Everything works as we expect. We'll just kill this. We're going to put the PCA back for now, but we may take it out again in the future. So let's go ahead and look at our first attempt at threading this work. Now, when we look at this script, and by the way, when I'm doing my exploratory data science, I always start with everything just at defaults, the simplest way to possibly write it. I have a for loop over my CSV files, etc. And then once I have things working and I'm satisfied with the results, we can take a look at the results really quick. Here are the plot outputs. I'm saving them as PDF format because I like vector drawings. I can just right-click and download, and it'll download it to my computer. Click it, open it, and we can see the plots here. Fantastic. Yeah, the first thing I do is I'll make sure everything's working, everything's to satisfaction, and then I look for the most parallelizable kind of independent chunks of work that I can possibly find in order to start parallelizing. And here, a great example is just that each CSV file is processed independently, right? Each iteration of this for loop has nothing to do with any of the other iterations. I'm loading my own CSV file. I'm doing data processing that has nothing to do with the other data in my data set. And then I'm writing the data out to its own result. There's no contention between different CSV files. There's no like globally shared state. Each thing is kind of isolated. And that is what we call an embarrassingly parallelizable workload. And it's what we really, really like, because it means that we can do very simple things. For instance, we can do this run threaded loop approach, which is going to be very similar to what we saw before. I'm going to squeeze these out so we can see the stuff in the actual screen. We're still going to have that for loop over the CSV files. We're not going to change anything about load CSV or process data. There is 2 things that we're going to change. The first is that we're going to use threads.addThreads. And what this does is it will split up the files that we are iterating over. And it will do things like assign every 8th one to the first core, and then shift over by 1 and every 8th one to the second core, then shift over by 1, every 8th one to the third core, etc. It just takes your iteration space and divvies it up amongst the different threads. And in order for this to have any effect, of course, you have to be running Julia with multiple threads. On JuliaHub, this is done automatically for you. So if I just run Julia and I say, hey, threads, how many threads are you running with? It will say the number of cores that are currently in your workstation. So in this case, 8. On your local machine, you probably don't have this set up automatically. On JuliaHub, this is set by having an environment variable called JuliaNumThreads set. It automatically sets it to the number of cores that are in your machine. On your computer, you can either set this environment variable, or you can run Julia with the -t option. I'm going to close top for now. If you look at the help for Julia, the -t threads will, you can set the number of threads that you're using, or you can set it to auto, which will be the number of local CPU threads. I usually just use auto, but yeah, that's how you get Julia to start up with a certain number of threads. And then when you use threads.addThreads, it will automatically split things up across the for loop. So other than that, the code is basically the same. There is one thing that I added up here, which is if you're running this at home and you forget to set -t, it won't even run. It's just going to be very opinionated that it should be run with threads. And then the rest is pretty much the same. We include the common code. We set our input and output directories. This piece right here is just to process one CSV file first. And the reason for this is so that our timing, it does not include that initial compilation cost. Anyone who has spent any amount of time trying to benchmark Julia code will doubtless run into the issue that they try and benchmark the very first time they run something, and the runtime seems quite high. That, of course, is because Julia is a just-in-time compiler. So the very first time you run your code, it will be doing a lot of compilation. But then the second time you run your code, it'll be much, much faster because it doesn't have to do that compilation. It already has the native code cached in memory. And so from there, we come into here, we do this threads.addThreads stuff, and there's one other difference. And that difference is that we are not calling plot data inside of this threads.addThreads loop. And the reason for that is because the plotting backend that we're using, GR, is not thread safe. And what that means is we cannot generate multiple plots on multiple threads. This is a pretty common restriction for complex C or C++ dependencies. There are many packages that are not thread safe. And so in order to deal with this, we generally have to do all that work on one thread. Now, the threads.addThreads macro here, this thing that's parallelizing my for loop, it doesn't really give me much flexibility in terms of where things are run. It's just going to do the dead simple thing of take all these files, split them up amongst the n different threads, and have them chunk through. And so what we're going to do is we're going to, instead of plotting the threads inside this thread loop, we'll take the results, push them onto this array, and then at the end, we'll have a single serial loop that loops over them and plots them all out. So in essence, what we're doing is we're forcing this chunk of code to be run serially at the end after all of the results have been calculated. So let's go ahead and see how long this takes. So this has a lot of benefits. The simplicity of threads.addThreads is really nice because, as you can see, it's hardly any change to my code at all. And yeah, let's open up top to make sure that we are actually going to be using more than a single thread. So Julia is loading all the packages right now. It's nailing a single core. And pretty soon we'll see that it starts to actually process things. Another interesting thing that you should always be aware of when you are dealing with multi-threading or parallelization is that reasoning about the order that things happen can be quite difficult. So when we run this, we will see that we do not, in fact, process CSV1 and CSV2 in order. You can see that the order seems quite arbitrary. And that's because different threads are executing at different times, and also the way that the values are divvied up is going to be completely up to the scheduler. And you can see now that we are using quite a bit more CPU. We're crunching through things quite a bit faster. It's not perfect. You can see we're not, perfectly balanced at 800, but we're generally over 400, over 500 most of the time. And now you see we've dropped back down to 100%, meaning we've dropped down to a single core. And this is most likely because we have actually finished the processing, and now we're just writing out all the results. In fact, what I'm going to do is I'm going to add an info here for future runs. Writing out results. And what we can see is that it finished processing all 30 of these files in 45 seconds, averaging that out to about 1.5 seconds per file. If we scroll up, we see that the serial did it in about 75 seconds, 2.5 per file. So we went from 75 seconds down to 45 seconds, almost a 2 times speed up. I'm actually going to also calculate this this results writing. T results equals elapsed, begin, all of these, and then we'll print that out at the end as well. Results writing was seconds. All right, we'll run that again, and I see that there are some questions in the chat. Diego asks, how can we know what is thread safe? Excellent question. The true, most general answer is you can't. You just run your program, and sometimes there are bugs or it crashes. However, reality is a little bit better than just that extremely general statement. Many packages will advertise their thread safety, and in particular for things like plots, it actually has some safety rails for you. If I say using plots, plots has this notion of a backend. In this case, it's set to the plots.gr backend. If I were to spawn, I believe this will work. This is the first time I've tried this, but we'll see. If I were to try and run plots.backend on a separate thread, see, is that going to work? No, it still says GR backend. Okay. What happens is plots complains that there is no backend that is configured when you run it on a separate thread, or that the backend is misconfigured. It won't crash your program, meaning like it won't seg fault or something like that. But what it will do is it will stop execution, and it will say, hey, you're trying to write out a plot, and I don't have a backend that can do that. It is possible to write plots in such a way that it could do that. It could load multiple backends and all that kind of stuff, and there may in fact be recipes for that online that I am just not showing here because it's more complicated. But the fundamental issue of there being things that cannot be run on multiple threads will always be true as long as we have C and C++ and these kinds of low-level libraries that can be written in thread unsafe ways. There are also ways to write Julia code that is thread unsafe, of course, where you have global state that's getting mutated by multiple things. In general, the way to deal with this is, first off, you start by parallelizing things that are as isolated as possible. And then secondly, you pay attention as you are parallelizing your code for things that seem fishy. For instance, if you parallelize your code and suddenly it is calculating the completely wrong results, there's a good chance that there is some state that is getting mixed up somewhere. Finally, of course, as you're using your packages, if something's going wrong, you just start looking through your packages and see, okay, is this thread safe? Is that thread safe? Is that thread safe? Over time, you will start to have a list of things in your head that you know are thread safe. For instance, you know that the CSV loader is thread safe, and you know that that all these data processing functions are thread safe, etc. People who are writing new packages are constantly improving the thread safety of their packages, because multi-threading is becoming more and more common in the Julia world. Yeah, unfortunately, there's no way to guarantee that you're only loading thread safe packages or such without actually going through and inspecting them manually. Miguel asks, what is the right use of PMAP compared to the methods you show here? Excellent question. PMAP is part of distributed, which is slightly different than the threading module. Distributed is a way to run computations across multiple Julia processes. And you can, of course, run multiple Julia processes on a single machine and get a very similar result to the kind of stuff that I'm showing here. However, that kind of processing is going to be geared more towards, I want to run multiple Julia processes across multiple machines, more like a cluster mentality. You can do it on a single machine. You can also do it on multiple machines. And the setup and steps you have to take is slightly different than what we're doing here. For instance, with multiple threads, because it's all happening in a single process, I only have to include code once. I only have to load a package once. And then I can have multiple threads running around inside of my single process, making use of all the packages that I've loaded. With a distributed and a kind of PMAP style methodology, you have to load things multiple times. You have to be a little more careful about where your code is stored, because if I'm running code on this machine and I submit a job to another machine that's over the network somewhere, I have to make sure that the packages are installed on both, et cetera. It's a little bit more work, a little bit more overhead, but the gains can be even larger because, of course, if you have 32 machines, each with 8 cores, you can get a much, much larger degree of parallelism. I have seen others use macros from distributed package for multiprocessing. Is it better practice to use thread macros? That's going to be melded into Miguel's question above. Distributed and threads are two slightly different approaches to the same problem of parallelization. My personal standpoint, my personal preference is to use threads first if you can, because it's going to be a little bit less work in general. However, the two big caveats do apply, which is that, first off, some things are thread unsafe. So if you have multiple threads and something's thread unsafe, you're trying to use a library that's thread unsafe, distributed could be a better approach because each Julia process could be running with a single thread, for instance. Bottom terminal's off screen. I hope I shifted that up for you. Thanks for the heads up, Alex. Javad says, the difference between serial and threaded parallel is just in for loop. It is not necessary to define different types for variables and functions. Great question. Right now, I've only shown the threads.addThreads macro that parallelizes for loop. The next thing we're going to look at is a slightly more flexible way of threading, something that will allow us to get a little bit more performance out of what we've done so far and is much more flexible. Simon asks, do you know if Gadfly is thread safe as well? In general, what is the best plots package suitable for multi-threading? So I have not used Gadfly in a while. I don't know if it is thread safe or not. My best guess is that there is an invocation that you can use with plots.jl in order to make it thread safe. I would have to go and look at the plots package, but in general, for these kinds of things, if it's not clearly laid out in the documentation, the best thing to do is to go onto Slack or to go onto the GitHub issue tracker and ask these kinds of questions. What we're going to see is that even though in this threaded for loop, where we have this for loop that goes run in parallel and then we run results, looking down here, it looks like total runtime is about 46 seconds, and then results writing was 15 of those seconds. So our results writing is that is a pretty decent chunk of time. But one of the issues here is that this is not being overlapped at all. We are running this for loop completely, and then once it's all done, then we start writing the results. But the very first result is actually available much earlier than that. So if we could overlap these two, start processing the results as the threads are still running up here, that would be much more preferable. And so what we're going to do is we're going to see how we can do that by using something other than this threads.addThreads macro. Coming back to my presentation, we'll just look real quick at what this looks like. So I'm going to minimize this, bring this over again. So what we're going to do is we're going to create we're going to give ourselves the ability to create something that looks like this, where we have our data coming in and we have kind of multiple chunks of processing, and processing 1 can generate outputs that get sent to processing 2 and 3. Processing 2 depends on things from processing 1, et cetera. We have this kind of directed acyclic graph, as it were. And what this graph is going to do is it's going to give us the ability to have each of these processing steps be happening in parallel. And we can, in fact, even have multiples of these steps processing in parallel. So not only can processing 1 finish, and then processing 2 starts up at the same time as processing 1 starts with a new piece of data, etc., things like that. The reason why we want this is because there are scheduling inefficiencies that can occur with the @threads macro. So here's an example where we have 15 work units that are spread out across the 4 different threads. These work units may take different amounts of time. This is a graph where time is increasing to the right. And what we see is, thread 4 is the lucky fellow that only gets 3 work units applied to him. And so once he finishes his work, all this time here is we would consider wasted, especially if there's more work that starts over here to the right that is waiting until all of these work units have finished processing. What would be really great is if this work unit right here in the top right could have been given to thread 4 once thread 4 ran out of work to do. So these kinds of scheduling issues and such, these are all kinds of things where we can see more and more how threading and parallel processing is kind of this complicated problem where we really have to think about how are we feeding our CPUs, which are these hungry engines that want to process through data. How can we feed them more efficiently? And so the way that we'll do that is I have this threading playground, file, which will basically do that little directed acyclic graph thing that I showed above. We're going to create these things called channels. For those of you who have never used these before, channels are basically just, they're like pipes. I push something in one side, and then I can take it out at the other. So here, let's go ahead and run this, switch back to our Julia REPL so we can see what's going on. Here I'm going to create a data in channel, and I'm going to create a thread with threads.spawn. And this is just a chunk of code that will send 20 pieces of data through. I'm going to put say this thing called index through, and it will tell me when it's sent it through. And then once it's done, we close the channel in order to signify to future people, like, hey, nothing more is coming down this pipe. So because I create channel with the number 10 here, it can hold 10 objects. I could create it with no number, in which case it can hold 0 objects, and it just, when you try and put something there, it waits until someone takes it from you. I could also put a very large number so that it can hold basically infinite objects. It's up to you how you want to design your code. Then I'm going to create a processing 1 block, which is going to take from that data in, and then it's going to do some processing on it, and then it'll put that data on these 2 channels I've created here, things that are those directed arrows that I had before, the processing 1 to processing 2, and processing 1 to processing 3 channels. So I can run these. And what you see is when I ran this, it started off that task, and then it immediately printed out, hey, I sent 11. And that's coming from up here. And the reason is because the channel was full after pushing on 10 objects. And then when I ran this, it took 1 object from data in, which allowed this thread to start sending things again. So you can see we have this kind of flexible scheduling going on, where one task can be running at the same time as another task. One task may stop because its buffer is full, but as soon as things start taking things out of that buffer, it'll start running again. And then finally, I'm going to start up processing 2 and processing 3, which are going to start taking from processing 1, and then processing 3 is going to print stuff out as it receives things from all the others. So let's run these. When I run this, boom, things can just flow. And the reason is because processing 3 is taking stuff from processing 2 and processing 1, which are in turn taking things from that original data thing. And we can see that we're getting data as we expect with like the squares, where I have 1, then 4, then 9, et cetera, et cetera, et cetera. And things kind of flow. The way that data flows through here is always going to be through channels, because these are the kind of fundamental asynchronous communication blocks that we'll be using in our threading and asynchronous and parallelized ways of speaking. And in fact, with distributed, where you have multiple computers, there's also a channel-like object that you can use. I see a question from Brian, which says, is there a way to have the channels automatically closed in a block? That's a great question. Something like a channel open, like a channel do block. I don't believe so, but that's actually that would be a pretty useful idiom. So we could probably build that fairly easily. Feel free to open an issue on the GitHub tracker, actually, because I think that would be useful for things like this. The main issue, of course, is how do you pass that data in object that you create to other channels, but there may be a way for us to do it conveniently. Great, so now that we've seen the kind of building blocks of this, creating channels, putting things on the channels, taking it from them, etc., we're going to quickly go over our run threaded with workers. So this is going to be pretty similar to what we saw with the threaded loop, with the exception that each of the pieces is broken out into its own little task that we are creating with this threads.addSpawn. So as usual, we have threads, we have include, we have the get scratch stuff, we have the pre-compilation, and then we start the timer to see how long this is going to take. And what we do is we immediately start with creating that data in channel, just like before, and we're going to have it load up to n threads amount of CSVs at a time. The main reason I have this as not just an infinitely sized channel is because if my data reading in is faster than my processing, I don't want to fill up my RAM with just a million CSVs that it's reading in. In this case, there's only 30 CSVs. I know I can read them all, but in general, that may not be the case. So what we do is we limit this so that the CSV loading will actually stop after a while. Now, inside this threads.spawn, you'll see I'm actually using a threads.threads. So here I'm parallelizing even this task so that I can load multiple CSV files at once. This is totally valid. You can do this. And this is basically just going to allow us to have n threads loading CSV files and pushing them into this channel. But if the channel gets full, then they will pause. So it's a way for us to basically load as many CSV files as fast as we can up until we're actually full. We actually have enough files that we're processing. Next, we're going to create a data processing thread, and here we have a for loop that's going to spawn n threads, where each thread is its own threads.spawn. And this is going to do the very similar thing where we take from data in, we run process data, and then we push results onto another channel. Then finally, down here, we have a loop that is not threaded. It's running on the main thread. And what it's going to do is it's going to take values from results and plot them out into a file. Just a few simple, or a few bookkeeping things. We always want to close a channel when we're done using it. So for instance, in the CSV loader, we close the data in channel once our CSV loading has finished. Down here, when we're processing the results and pushing them onto results, we add a little asynchronous task that waits for all of those processors to finish, and then it closes results. The reason is because we always want to signify to further tasks downstream, hey, I'm finished, there are no more values coming down this pipe. And that will trigger things like the isOpen function and such to say, we're done processing, we can gracefully exit now. We always want to wait on tasks, because if there is an error that gets thrown on a task, it's only going to be shown when you wait upon it, unless you purposely catch it or something. So we always want to do this just so that we can always be assured that everything is running cleanly. And so if we were to actually run this, what we'll see is we'll get a runtime that's pretty similar to what we saw with the threaded loop. It will probably be a little bit faster. The main reason being because our data processing, our data loading, and our results writing can all be thoroughly overlapped now. There's no artificial separation of all the different pieces. And with that, I think I'm pretty much running out of time. If you guys have any further questions, feel free to ask. I'm going to let this thing run in the background so that we can see what it looks like. But to answer some of those questions that we went over at the very beginning, the way that we can measure how successful we've been is through things like we can look at the CPU usage and make sure that, hey, we're actually close to the theoretical maximum most of the time. So you can see here that we're staying above like 500-600 most of the time. So that's decent. It's not perfect, of course. There's probably different inefficiencies in different places that we can fix through more careful profiling of this code. And of course, as you are working on your own projects, you're going to want to do things like use the Julia profiler, look at your system usage. You'll want to look at things like disk usage. Is your disk being maxed out and you just can't read the data fast enough, et cetera, et cetera, et cetera. All these different pieces in these complex systems that we call computers. So you can see here that pretty quickly it finished loading all 30 files, and now our CPU drops down to 100%. So I believe we are still bottlenecked by that results writing. Yep, and you can see we get almost the exact same amount of time. Now, if we were to use the larger CSV files, we actually get a much bigger difference between the three approaches. And that reason is because the plotting then becomes a little less dominant in time. So I'm going to minimize this a little bit, drag it on here. So in my tests with the big CSVs, what we find is that serial takes about 680 seconds, threaded loop takes about 300, and threaded workers takes about 200. Sheikh asks if you know what is the memory overhead of Julia channels in Spawn compared to Go channels plus Go routines. Is a thread spawn similar to a Go routine? A Go routine is a little more similar to the async block that I showed before, which is a extremely low overhead, an extremely low overhead concurrency primitive. So like this thing. This doesn't actually use a separate thread. I don't know what the comparison between an actual Go thread is to us. I know that we are low overhead, but not as low overhead as like the theoretical minimum. So there is some ongoing work for applications like this where you have kind of data that's independent and you want to spawn a bunch of different threads for it, et cetera. But that work will probably appear in Julia 1.7 or 1.8. The overhead for these threads that we're launching is quite small. If you measure it, it's going to be, millisecond style, like single-digit milliseconds, probably, maybe a little bit less depending on your machine. So you can spawn threads without fear, but you probably don't want to spawn a thread to just like add two numbers. That's just going to be too much overhead. But any kind of realistic work that you're doing inside your threads, the thread spawning will be much smaller than that. I don't know what the runtime memory requirements are. I don't know that off the top of my head, but it's fairly easy to benchmark, so should be pretty easy to find. And Javad, just in case I didn't explicitly say this, no, you do not need to define different types for your variables and functions for parallel versus serial. You just need to run them inside of these things like threads.atSpawn or threads.atThreads. With the caveat that if there are things that are thread unsafe, such as a C library that you're using, you may get unexpected results. So start with your pure Julia code and work out from there. Gail asks if it works in Pluto. Yes, it does work in Pluto, but you have to have Pluto started with multiple threads. Rigoberto asks, are most packages to import CSV files multi-threaded already? CSV.jl is, and that's the one that I use the most because I have found that it is by far the fastest. So I would just suggest that you use CSV.jl. It is already multi-threaded and it's very, very fast.
I just want to say thanks, everyone, certainly for joining us today. We appreciate your time, and thank you to Dr. Saba. If you have any further questions, please feel free to ask your questions on the Julia Discourse channel or if you're working on a commercial or production application, please contact us at sales@juliacomputing.com. Thanks again for joining us, your questions, and your continued use of the Julia language. Happy St. Patrick's Day, and have a great week, everyone. Thank you so much.